A solved protein structure is a constrained mathematical hypothesis, a calculation of the most probable arrangement of atoms based on a specific set of diffraction data. X-ray crystallography is an exercise in probabilistic inference. The atomic coordinates we rely on are derived entirely from the probability that a specific electron density distribution caused a specific pattern of scattered light. Every phase of this process is governed by distinct statistical distributions. This begins the moment physical photons strike the detector array. To understand how we map molecules at the atomic level, we will trace the mathematical journey of a single diffraction spot, starting from the point of photon impact all the way to the final structural model. Along the way, we encounter a hard limit. While classical error models handle strong signals reliably, they produce undefined results when weak data and high background noise generate physically impossible negative values. The only way to rescue modern macromolecular structures from this collapse is to abandon classical frequency-based mechanics and process the data through Bayesian inference. The data collection process begins in a non-deterministic environment. Incoming X-ray photons do not arrive at the detector in a perfectly timed, predictable stream. They strike randomly and independently. This chart shows the probability distribution for measuring a specific number of photon counts. Because the photons arrive as discrete, uncorrelated events, they follow a Poisson distribution. This distribution is driven entirely by a single parameter, the expectation value, or the true average count rate. For weak reflections, averaging 1 or 3 counts, the distribution is highly asymmetrical and restricted to discrete integer bins. Notice how the shape of the Poisson distribution strictly depends on how many events are counted. As the expectation value increases to 12, the shape widens and shifts right. Right around an expectation value of 10 photons, a crucial mathematical transition occurs. The distinct staggered bins begin to smooth out, approximating a continuous curve. This graph illustrates that continuous limit, the Gaussian normal distribution. Here, the overall shape remains symmetric regardless of the true value, with the width defined by the variance and standard deviation. For a Poisson process acting at a Gaussian limit, the variance is exactly equal to the expected count. This means that as the number of recorded photons goes up, the relative error of the measurement drops drastically. For strong diffraction spots, the physical reality of random photons automatically smooths itself into these mathematically friendly, highly predictable normal distributions. But real crystallographic data presents a theoretical problem. The underlying probability distribution functions for structure factor amplitudes, like the Wilson distribution, are heavily asymmetric. They are not Gaussian. So why are crystallographers allowed to use Gaussian tools like standard deviation and chi-squared metrics to analyze this non-normal data? This chart illustrates the justification, the central limit theorem. Look at the blue parent distribution. It is heavily skewed, with the mode pushed far to the left of the mean. If we randomly draw from this parent distribution and sample it 5 times, the resulting distribution of those sample means, shown in green, begins to shift. Increase that to 10 samples, and the red curve emerges. The distribution of the sample mean inherently forces itself into a normal shape, regardless of the extreme asymmetry of the source data. The variance of this new normal distribution scales inversely with the number of samples. High redundancy, measuring the same reflection multiple times, drastically tightens the precision of the mean. As long as measurements are independent and highly redundant, the central limit theorem safely masks the messy physical asymmetry of the raw data, allowing our classical statistical tools to operate smoothly. That smooth operation ends at the margins of the dataset. We have to address what happens to the math when the signal is incredibly weak. To accurately measure a reflection, we must subtract the background scatter from the total measurement to isolate the true peak intensity. Consider a specific scenario for a very faint reflection. We record a weak peak measurement of 4 counts with an error margin of plus or minus 2. We subtract a background estimate measured nearby, which comes in at 9 counts, plus or minus 3. Because these are independent variables, we run them through the classical error propagation formula, adding their individual variances together. The output is mathematically consistent with the input variables, but physically impossible, an intensity of -5, plus or minus 3.5. This creates a hard mathematical stop. To convert this intensity into the structure factor amplitude needed to build the model, we have to take its square root. The square root of -5 is undefined in this context. The classical pipeline fails. The simplest response is to throw out the negative reflections, but statistically this is a failure. By deleting it, you are throwing away the definitive, valuable knowledge that the reflection is completely absent of a large signal. Classical, frequency-based statistics break when noise eclipses the signal. To process this data without destroying information, we need a completely new mathematical framework. The solution to the negative intensity problem is Bayesian inference. This is Bayes' theorem. It calculates the posterior probability of our model by multiplying the data likelihood function by our independent prior probability. The blue prior probability term represents our hard-coded chemical knowledge. Independent of any specific experiment, we know that structure factors must be positive and follow specific known distributions. The green data likelihood term represents the statistical probability that our detector would observe a mathematically negative intensity, assuming our structural model is correct. The equation forces the weak, paradoxical experimental data to be constrained by strong prior knowledge. It evaluates the measurement through the lens of physical reality, yielding a reliable, positive structure factor without discarding the underlying observation. Bayesian inference rescues the structure. It anchors the extreme deviations of weak statistical noise to established physical boundaries. But Bayesian logic carries an inherent risk. If we actively restrict our data based on our prior assumptions, how do we avoid blinding ourselves to completely new discoveries? The counterbalance lies in the math itself. An incredibly strong data likelihood, representing overwhelming physical evidence, will statistically overpower a confident yet incorrect prior probability. We can see this dynamic clearly in Dorothy Hodgkin's 1949 structure of penicillin. At the time, contemporary organic chemists held a massive prior assumption that a 4-membered beta-lactam ring was chemically impossible, but Hodgkin's diffraction data was undeniably strong. The sheer statistical weight of the experimental evidence forced the scientific community to accept the ring's existence, overriding their ingrained expectations. The power of modern crystallography lies in this exact mathematical balance, using prior knowledge to filter statistical noise at the margins, while allowing undeniably strong experimental evidence to correct and expand our chemical axioms. Across the physical sciences, standard least squares minimization operates as the default algorithmic solver. When fitting a model to data, the unquestioned instinct is to minimize the sum of the squared residuals. That ubiquity rests on a specific mathematical foundation, the central limit theorem. Least squares optimization is strictly valid only if the errors in measurements are independent, random, and follow a normal distribution. In the early stages of crystallographic structure determination, those conditions are rarely met. An initial hypothesis is usually aggressively incomplete. We might be missing entire structural domains or solvent networks. The resulting errors are highly correlated. If we force a least squares algorithm to fit an incomplete model against the observed data, the math assumes the model is physically complete. The algorithm will warp the available atomic coordinates to fit random noise peaks, attempting to account for the scattering contributions of the missing mass. To solve complex structures accurately, we must transition to maximum likelihood methodologies. Applying least squares to non-normal errors invalidates the structural solution because it fails to model the errors present in our own hypothesis. Maximum likelihood shifts the mathematical target. Instead of minimizing a residual, the objective is to maximize the probability of observing our experimental data, given the parameters of our structural model. In practice, this means computing the joint probability for thousands of individual structure factor reflections. Multiplying thousands of independent probabilities together yields vanishingly small numbers that cause immediate computational underflow. We bypass this limit by transforming the problem into log likelihood space. By taking the natural logarithm of the probability function, we change the operational landscape. These charts display an actual crystallographic probability distribution. The top graph shows linear probability, and the logarithmic equivalent sits below. Unstable multiplication of probabilities translates into a stable summation of logarithms. This mathematically expands the peak, making it easier for an algorithm to target. The numerical maximum for the structure factor f remains identical in both spaces. Operating in log likelihood allows computational solvers to add up infinitesimal fractional probabilities rapidly, without losing track of the true likelihood peak. Formulating a proper likelihood function that correctly accounts for non-normal physical errors is complex. To make these functions actionable for an algorithm, we have to simplify them. We do this by expanding the log likelihood function into a Taylor series. Take a complex probability distribution representing our generalized likelihood. We apply the Taylor expansion directly around the function's maximum peak, x0. The first-order linear term defines the slope of the curve. Because we are expanding exactly at the maximum peak, the slope is 0. The entire linear term mathematically drops out of the equation. We are left with the critical second-order term. This term dictates the curvature of the peak. Because we are at a maximum, the curvature is negative, forming a simple negative quadratic. We have replaced a complex likelihood function with a straightforward inverted parabola. If we move out of the logarithmic space and exponentiate this remaining quadratic form, the resulting equation matches the standard Gaussian formula. This derivation positions the normal distribution as a localized parabolic approximation of a generalized probability function. It also positions classical least squares minimization as a specialized subset of maximum likelihood. Least squares is only valid if we are at the very peak of our distribution. Everywhere else, we have to build custom, conditional error models. Let's apply this to a specific problem. How do you optimize a hypothesis when a significant percentage of the atomic sequence is missing from your model? We start by formally splitting the true structure factor into two pieces, a known component generated by our partial model and an unknown component representing missing atoms. The known component establishes a defined vector in the complex plane. We cannot assign definitive vectors to atoms we haven't found. Instead, we model the unknown component as a statistical random walk spanning out from the tip of our known baseline vector. This random walk forms a diffuse, two-dimensional Gaussian probability cloud. The missing mass exists somewhere within that spread. Because we lack the coordinate data to know the exact phase angle of the missing atoms, we mathematically integrate the unknown phases out of the probability cloud. This operation yields a conditional probability distribution, known as the SIM distribution. This chart plots the SIM weight, an objective metric grading our partial model's reliability. The green line represents the modified Bessel function ratio. As the variance of missing mass increases, the algorithm uses this ratio to downweight known phase contributions. Through the SIM distribution, we have successfully parameterized our own incompleteness, building a mathematical mechanism to objectively handicap our confidence. We can push this probabilistic framework further, right to the experimental limit of the data pipeline. Up to 5% of recorded reflections can be so weak that subtracting background noise yields a negative intensity count. Standard error propagation fails here. Taking the square root of a negative intensity to find the structure factor amplitude results in an imaginary number. The classical response was to delete these reflections. But selectively discarding weak data strips structural information and introduces systematic bias into the final electron density map. We salvage this data using Bayesian Inference. Look at the top row of this data table. An observed intensity of -16 breaks the classical square root formula, returning no result. But the Bayesian posterior correctly resolves the math, returning a usable, positive amplitude of 1.34. It accomplishes this by combining the messy likelihood data with a strict physical prior, the reality that a scattering event cannot have an amplitude of less than 0. These curves show the unconditional Wilson distribution, the specific mathematical operator enforcing this bound. By mapping the Bayesian equation over this prior, the math restricts the distribution to positive space, preventing probability from drifting negative despite raw detector counts. There is a trade-off. The Bayesian posterior yields a positive amplitude, but assigns it a massive standard uncertainty. By applying physical priors, we save boundary data, eradicate systematic deletion bias, and quantify our lack of confidence in weak signals. Today, structural crystallography has permanently transitioned away from rigid deterministic refinement, moving to a flexible framework built entirely on likelihood probabilities. In the past, the classical pipeline forced incomplete models onto truncated datasets. Maximum likelihood offers the flexibility to explicitly model the imperfections of our own physical experiments. We use sim-weighted phase probabilities to insulate the structure against missing atomic mass, and we deploy Bayesian posteriors to rescue weak, noisy detector intensities. The algorithm explicitly accounts for structural incompleteness and measurement errors by incorporating them into the conditional probability distribution. However, these likelihood models depend entirely on the validity of the chosen priors. A Bayesian prior must be rooted in immutable physical properties, like the statistical mechanics of the Wilson distribution. If a prior is based on subjective assumptions, the likelihood model will optimize a false result. Defining the limits of our knowledge through variance and standard uncertainty remains the most rigorous method for determining the atomic structure that actually exists.